Okay guys, so this is video 2 and I'm going back to the pizza pen problem. So we used the information initial temperature was given for 50, room temperature it's 70, and again initial temperature it's always the highest one, and the temperature of the pizza pan after 5 minutes was 300. So what I did with those information, I used the Newton cooling law. So I copied the formula and I start plugging in the given information. Okay. So like I mentioned, with any type of problems which we solve in section 6.8, you always need to know K, which is our growth rate or decay rate. The only variable which your equation should have is T. So I plug in everything what was given from the problem into Newton cooling law. And again, we end up with the equation where constant k was not given. And u of t I replace with 300 because after 5 minutes, the pizza pan temperature was 300. So u of t I replace with 300, and the variable t, where you guys see here, I put 5 minutes. And our equation end up to be 300 equals 70 plus 380 ek times 5. We use that equation to solve it for k, which is constant. And of course, it's exponential equation, so we need to change to logarithmic. And we end up with the constant's negative 0.10042. How I know we're on a good track? First of all, the constant k for Newton cooling law, it should be negative. So we end up with negative. And also, I solved that problem before, so I know we good. So now I update the Newton cooling law formula into our problem. So u of t, which is the temperature of the heated object with time, you can find out by using the equation 70 plus 380 e negative 0.10042 t. Okay, 380, and that from this part, initial minus room temperature. So now we can go to part A, and they ask you to find the time when the temperature of the pen it's 135. So let's just update that. So not this. So find T when the temperature is equal 135. Okay, so what we're going to do, we're going to use the equation which we just built. We're going to replace u of t with 135. And solve this equation for t. Okay, so what is the time when the pen has 135 Fahrenheit temperature? Okay, so we need to isolate this part, okay, to change it, the exponential equation to logarithmic equation. So I'm subtracting 70 from both sides. That will give me 65 equal 380 e negative 0.10042 t. Again, before I attach ln, I need to divide both sides by 380. And that will be 65 over 380 equal e to the power of negative 0.10042 t. 65 over 380, if this is nice decimal. No, so I'm going to keep it as a fraction. I'm not going to reduce it because I will plug in everything to a calculator. So now we're ready to attach ln to both sides. Ln of 65 over 380 is equal to ln of e to the power of negative 0.10042 t. Solving those equations right now should be quick. ln and e cancel. So we have ln of 65 over 380. It's equal negative 0.10042t. And to get t by itself, we're just going to divide both sides by negative 0.10042. And we're getting, and again, when you plug it in a calculator, plug it in that way, and you're getting that t, it's equal 17:58 minutes. So it takes, let's round it to 18 minutes. It takes about 18 minutes to that pizza pan to cool off to 135 Fahrenheit. But if you got to read the problem, they asking at what time. Okay, so we have to be more specific. It takes 18 minutes to cool off to 135. What time that will be? We remove the pizza at 5 p.m. So after 18 minutes, it's going to be 5:18. So we remove the pizza at 5 p.m., right? And it takes 18 minutes to cool off to 135 degrees. So the time will be, it's just 5:18. So they want specific time here. Okay, so we did that. Let's talk about part B. In B, they ask you to find the time that needs to elapse before the temperature of the pan is 160. So in B, you guys will do the same thing for B. You have to find the time, okay, when the temperature of pizza pan is 160. Okay, so you will solve exactly the same way. So you will solve, just, I will leave that, solve the equation for t. So you solve 160, it's equals 70 plus 380 e to the power of negative 0.10042t, and you will solve exactly the same way like in part A. Follow the same steps and you should end up with t equal 14.3 minutes. Determine the time. So they're not asking what time exactly that will happen. Okay. And C, it's important. See, they asking you, and let's just read that. What do you notice about the temperature as time passes? What do you notice about the temperatures as time passes? So as time passes, you guys see that the temperature is dropping. After 18 minutes, temperature is 135. Okay, after 40 minutes, temperature is 160. So with the time, the temperature of the pizza pan is decreasing, but the most important that the temperature approach the room temperature. So that temperature will be approaching actually 70 degree Fahrenheit because that's the room temperature. So let me just write this down for you guys. The temperature, and that's not just with this example, with any example of Newton cooling law. The temperature approaches the room temperature of our surrounding, which is 70. Eventually, you can try it after 30 minutes, plugging in into that equation 30 minutes or like 60 minutes, and you should start getting technically the same answer, which is about 70. About 70 Fahrenheit. Okay, so eventually with the time, the pizza pan will have a temperature personal to the room temperature. Last model is logistic model. I still have to talk about it. There are two models. One is increasing, the other is decreasing. And with logistic model, I think one example will explain everything. Okay, so you guys will practice them. Excuse me, for homework. Okay, so one more thing from this section. Okay, last one is the logistic model. Let me give you the formula. Logistic model, okay, and again, you don't need to memorize the formulas, just have them during the test, all of them in front of you. Make sure that you know what each coefficient explains, what represents. So the formula, it's P of t equal C over 1 plus A E negative B T. Okay, if somebody will look into that, okay, what formula is that? You just have one number, 1. Of course, E, it's also a number. Okay, so couple things. I'm going to explain everything, but the only variable is t. So your equation should only have t. Everything should have numbers. Okay, and A, B, C are constants. So A, B, C are constants. Real numbers, okay? So let's explain step by step. P of t, it's going to be the population after time. Again, after, it depends, 5 hours, 5 years. A, B, C are constants. And what we know about A and C, let's put it them separate maybe. A has to be positive, C has to be positive, and B, when B is positive, the model is a growth model. So the function will be decreasing. I'm sorry, increasing. Oh my God. Increasing growth model. So based on B, you're going to know if you have a increasing or decreasing function. Okay. When B it's less than 0, okay, we have the model is decreasing, which is decay model. So decay when B is less than 0. So why that B is super important? Because absolute value of B, okay, we call in growth rate. Okay, so again, can be positive or negative. Okay. What else we need to know? We need to know also what letter C represents. It's also very important. Constant C, it's a carrying capacity. So this is carrying capacity. So when we're talking about the population, okay, we almost all the time have the carrying capacity, okay? Or when we're talking about population of students in Pasco Hernandez State College, of course, we have that C carrying capacity, okay, which would be, let's say, I don't know, in the campus, maybe we can have maximum of 1,000 students. it's more probably at the time. Okay, you're going to the library, we have that carrying capacity, so that's what is C. Okay, carrying capacity. So logistic model can be growth or decay. Let me graph both of them. So let's talk about logistic growth model. It doesn't matter if you have graph of decay, we're still using the same formula. The only difference will be that one will be having positive coefficient in front of t, the other will have negative coefficient in front of t. So logistic growth model, so increasing function looks like this. So this is t, it's always your x-axis, and here we have population. Okay, so logistic growth model has two horizontal asymptotes when we're dealing with population, so we should not have something below 0. That's why you have horizontal asymptote at p equals 0 when population is 0. And the most important when we talk about that carrying capacity, which is C, that's the other horizontal asymptote. So carrying capacity, your graph should not pass over carrying capacity. Okay, so since we have increasing functions, so that carrying capacity, you may think about it's a limit. Okay, when time increase, so that's the maximum capacity we can have it in the population. And 2 points, this is point, of course, 0 comma po, so initial population. Between 0 and C, you will have half of the capacity, half of the carrying capacity. And I will explain in a second. You have inflection point. And I will write down what inflection point is. Okay, so this is how the function looks like. Let me just fix that. No, not like this. Okay, something like that. So inflection point, it's the point on the graph where the function change from being curve down to curve up. Okay, so here again, that's being graphed by hand. We should have a change like that. Okay, the graph being curved down to curve up, or vice versa. So point like that, when we see that change, we call inflection point. Okay, and we actually finding that inflection point a lot in calculus. So let me just quickly write this down. So inflection point. And that inflection point, what is important, is at half of carrying capacity. Okay, so right here. Okay, that should be right here. Half of carrying capacity is half of carrying capacity. Okay, inflection point. And inflection point is where graph changes from being curved up to being curved down. Okay, and vice versa. Curve up to be curved down. Okay, so here we have curve up to be curved down. I think I said that accidentally opposite before. Okay, so this is logistic growth model. So that's when functions increasing. And also we have logistic decay model. So let me separate them. I want to graph it because this is new for you guys. Logistic decay model. So here K will be negative. Okay, for logistic growth model K, it's positive. Okay, K will be negative, and let me graph it. So this is 0, this is time, P of t. Also, we have two horizontal asymptote when population is equal 0, and next one, the top one will be the carrying capacity. Okay. Halfway, we have 1/2 c, which is our inflection point. Just put that inflection point right here. And of course, somewhere on the top, you're going to have initial population. Initial population. Okay, since this model it's decreasing decay, so your carrying capacity is at the beginning. It's initial population is very close to the current capacity, and then function will be decreasing, so the population will be approaching 0. Okay, so this is how the graph looks like. Want to draw that correctly, that inflection point. Okay, something like that. I'm not perfect, but okay, it should be like this. Should be that switch here. So this is inflection point here. Better graph it's in the textbook. Okay. So the same formula. So this is logistic decay. Okay, so that's the difference, that here function decreased, over there function increased. So when function decreased, the population approaches 0, and when and we starting with initial population, which is close to the carrying capacity, which is your constant c. When model it's increasing, which is a logistic growth, actually our initial population, it's close. Again, it doesn't have to be so close to 0, but it's definitely closer to it's below inflection point, and with the time the population it's going to slowly approach the carrying capacity, but it will never pass. Okay, so here we go. Let's solve the problem. I'm going to pause and copy the problem for you. So hold on a few seconds. Okay, so I'm going back. So I copy and paste number 23, and this is from page 487 in your textbook. And we'll solve one problem. So let me just explain it. And just to practice logistic model, I'm going to add couple more problems so we can understand how that model works. So logistic model, and we have it, it's given by the formula, represents the percentage, so percentage, important, of households that do not own the personal computer T years since 1984. Okay, so represents the household that do not own the computer since 1984. So let's talk about it. Okay, this function definitely will be logistic decay, because with the time, again, we know that with the time, almost everybody, most people have the personal computer. So that means P which is percent of households who do not own the computer. So that number with time will be decreasing. So definitely decreasing logistic decay function. And we have to answer all those questions. Before we answer all those questions, I want to ask two. Okay, so let's just answer two questions. So my first question is first. So I'm asking, okay, question number one. What is the carrying capacity based on this example, of course. Okay, so don't forget that the carrying capacity, okay, that you're C, okay, so the number which you see on the top will be the carrying capacity, which is 95.4993. That's our carrying capacity. Okay, and number two, my question is, what is the, and I already mentioned that this is decay. So what is the decay rate? So going back to our problems, okay, when I explain everything, decay, it's B, it's constant B. So constant B, when we talk about constant, which is which affects how population increase or decrease, okay, it's always that constant in front of T, okay, so B is going to be constant in front of T. So you have to find in our problem the decay rate that's going to be the constant in front of T. Okay, so B, it's equal, and like you guys see, 0.1968. Okay, and has to be negative. Okay, and you can change that to percentage, which will be again the same as 19.68 decay rate percent. So why B I put negative? First of all, I know it's negative model, but don't forget that our original function has a minus here, okay? So since we don't have a minus, that means, again, B definitely it's negative because the formula is e to the power of negative and negative 0.1968. Together you get that plus, okay? So definitely when you have a minus in formula, your rate, it's the opposite of what you see. You see positive number, that means your rate will be negative. Okay, and when I talk about percentage, I put 19.68 decay rate, so I know that B is negative. Okay, that's just working with the formula. Now we're going back to the problem. Okay, okay, A, evaluate and interpret P of 0. P of 0, that means population when time equals 0. So which is our initial population. So we're going to figure out how many people did not have a computer in 1984, because they start doing that study in 1984. That means T equals 0 represents year 1984. Again, we need to read that. Okay, of course, not year 0, year 1984. That's when we start studying. So we need to find the initial population. Okay, so technically, how many people did not have personal computers at 1984? That's what they ask you. So how are we going to do it? Just replace t with 0. So we have p of 0 equal 95.4993 over 1 plus 0.0405 e to the power of 0.1968 times 0. Okay, and that will give us 91. So technically from here, guys, you end up with e to the power of 0, which is 1. So that will give you 95.4993. So with this logistic graph model, you have to do work to be able to see initial population. 1 plus 0.0405, which is 95.4993 divided by 1.0405, and we should end up with 91.8%. So what that means, 91.8% people did not have personal computers, which computers at home at, I'm talking about year 1984, right? Makes sense. Let's solve B. For B, give me a second. B. Use the graph utility to graph it. I'm not going to graph that by hand. Again, I'm not asking you to graph it with skipping B. We're not using graphing utility, everything what you need graphing calculator. So C, what percentage, so find P, what percentage of households did not own people, I'm sorry, let me just fix it, households. Okay, so in C, they asking what percentage of households did not own personal computer in 1995. So here we're talking about year 1995. So don't forget that when t is equal 0 represents year 1984. So year 1995 will be t equal 11. Okay, so that's 11 years since we start doing the study. Okay, so technically 1995 minus 1984 is 11. Okay, so to find that p, you're going to replace t from the equation with 11, not 1995. Okay, so we have p of 11 equal 95.4993 over 1 plus 0.0405 e to the power of 0.1968 times 11. Slowly evaluate that on the calculator. I'm not, I would say I won't, unless you have nice calculator, plugging in everything once. If you really want it, you need parenthesis here, fraction Barrett's division, parentheses here, and then you should be fine. So your answer will be 10, about 10. And of course, P it's in percentage, so 10%. Okay, so they asking 11 years from 1984, which is in year 1995, what is the percentage of household who did not have personal computer? 10%. Okay, definitely it's going to decrease. Makes sense. And do we have more? D. One more. In D, they asking in what year did the percentage of household that do not own personal computer reach 10%? I'm sorry, not 10%. Ooh, I messed up here. I read the answer of the previous one. Here, it wasn't 10. Do your work, guys, and you will end up that the solution of C is 70.6%. 70.6%. We're talking about 1995. We still people really don't own the computer at home. Not too many of them. So sorry, guys. I was just reading too fast. D. In what year did the percentage of household that did not own personal computer reach 10%? Okay, so here we know that P is equal to 10%, and we need to figure out time. So technically, at what year 10% of household still did not have computer? That's what they asking. So you need to solve equation for T. So we have 10. P of T, you're going to plug in 10 equal, where is that equation? 95.4993 95.4993 over 1 plus 0.0405 e to the power of 0.1968 t. Okay, we need to solve for t. Okay, a lot of work to be able to solve for t. What I recommended to start with cross multiplication. Okay, and multiply across. So we're getting 10 times 1 plus 0.0405 e to the power of 0.1968 t equal 1 times 95.4990, which is 95.4993. 1 times. Okay, so what I will do, I will divide each. I'm not sure if you guys can see that one. I will divide all by 10. So don't worry about that. So we end up with 1 plus 0.0405 e to the power of 0.1968 t equal 95 divided by 10. That will be 9.54993. Okay, what we have to do, you need to solve exponential equations. So don't forget that first thing what we need to do, we need to isolate this guy. Okay, we need to isolate it. So of course you cannot add 1 to 0.0405 because order of operations PEMDAS exponential first. Okay, so forget about adding. Eventually you guys see that they're not like terms. So we need to isolate the exponential part. So first what we need to do is subtract 1 from both sides. And we're getting 0.0405 e to the power of 0.1968 t. It's equal 9.54499 minus 1. So that will be 8.54993. And then last step will be divide everything by 0.0405. So we can get that e by itself, and we're getting e to the power of 0.1968t equal. Here when we divide it, we're getting 211.1094. And now to solve for t, which is exponent, you change exponential to logarithmic function. So we're attaching ln to both sides. And we're getting ln of e to the power of 0.196. Again, that will cancel. Equal ln of 211.1094. So we're having 0.1968t equal ln 211.1094. And the last step, divide each by 0.1968. 0.1968. Again, be patient with those equations. So t, it's equal, parenthesis here, and that will give you, if you guys plug in that on the calculator, you will end up with 27.2. Okay, so 27.2 years. Okay, but what year are we talking about? So we start the study with 1984. 1984. So 27 years after 1984. Okay, I'm just going to skip that point too. That will give us 2011. So in 2011, the population of households who still do not hold personal computers is 10%. Okay, so the answer is 10% of households do not own personal computers in 2011. Oh, my English, guys, in 2011 started correctly. Don't learn grammar from me. In 2011. Okay, I think it's time to finish that lecture because I cannot even erase it. In 2011, 10% of households do not own personal computers. Okay, and that's it. Okay, so now you guys ready, you have everything what you need to study for our final test, which will be next week. Soon you're going to see the study guide for your final exam. Okay, so this is the end of section 6.8. Okay, hope that will help you to study. Stop recording.